Your phone displays the time without hesitation. But time is invisible. So what is a clock actually measuring? A clock does not observe time itself. It compares one interval with something that repeats, sunrise after sunrise, a shadow crossing a mark, or an atom oscillating again and again. This is the story of how humans moved from shadows and flowing water to gears and atoms, searching for repetitions stable enough to share with everyone. The most obvious cycle was the day, light, darkness, then light again. Place a stick in the ground, and its shadow moves opposite the sun. The breakthrough was not the stick. It was marking the same shadow positions in the same place, so yesterday could be compared with today. A natural change became a scale that could be read again. In ancient Egypt, daylight and nighttime were each divided into 12 parts. Those early hours were not equal. A daytime hour grew longer in summer and shorter in winter. A shadow clock has serious weaknesses. Tilt the ground and the reading shifts. Move north or south and the sun follows a different path across the sky. The same clock also behaves differently in summer and winter. Clouds hide it, and at night it stops completely. A sundial could be useful without showing one universal time. People learned that a clock needed more than an object. It needed orientation, location, correction, and a shared method for reading it. Timekeeping was already becoming a social agreement. When the sun disappeared, flowing water offered another repeating process. Water escaped through a small opening while marks on a vessel tracked the changing level. Water clocks appeared in several regions, including Egypt, Greece, and China. They helped organize night watches, ceremonies, and even the speaking time allowed in public proceedings. But the flow was not perfectly steady. Pressure changed as the water level fell. Hole size, vessel shape, temperature, and dirt all introduced error. Better clocks came from measuring those failures and redesigning the vessel. For intervals longer than a day, the moon offered a visible cycle. From one new moon to the next takes about 29.5 days. But 12 lunar cycles are about 11 days shorter than a solar year. Without correction, a lunar calendar slowly drifts away from the seasons. Different societies solve this in different ways, adding an extra month, watching the sun, or combining several rules. A calendar was never just a copy of the sky. It was a system for managing mismatch. A day has 24 hours not because nature contains 24 identical pieces. An important foundation was the Egyptian practice of dividing daylight into 12 parts and night into 12 more. 60 minutes and 60 seconds connect to the base 60 mathematics developed in ancient Mesopotamia and later used by astronomers. 60 divides cleanly by 2, 3, 4, 5, and 6. Minutes and seconds did not begin as tiny marks on everyday clocks. They entered ordinary timekeeping as astronomy and mechanical clocks became precise enough to make those smaller divisions useful. Knowing a cycle is not enough to coordinate a city. People needed to record when to plant, gather, work, sail, or prepare for the next season. Once marks and writing preserved calendars, time moved from personal memory into institutions. Festivals, taxes, labor, and travel could be arranged on the same sequence of dates. That power was not neutral. Whoever controlled the calendar could influence when everyone else acted. Standardizing time became a technology of cooperation and also a technology of government. As towns grew, checking a private clock was not enough. One reference had to reach many people at once. A tower bell turned invisible time into sound. As mechanical tower clocks spread through medieval Europe, bells coordinated worship, markets, gates, and work. People did not need to see the dial to receive the signal. Those early clocks were far less accurate than modern ones. Yet they still transformed society because everyone could share the same error. A common standard mattered before perfect accuracy did. A mechanical clock does not let a falling weight spin its gears freely. An escapement releases the gear one step at a time, converting continuous force into countable beats. In the 17th century, practical pendulum clocks greatly improved accuracy. The regular swing of the pendulum became the clock's new heart. The pattern was unchanged. A clock still counted a repeating event, a shadow, flowing water, or a swinging pendulum. Humans simply kept replacing unstable rhythms with more reliable ones. Solar noon arrives at slightly different moments in towns east and west of one another. When travel was slow, each town could keep its own local time. Railroads changed the problem. If every station clock disagreed, timetables became confusing and safe scheduling became harder. A fast network required a shared clock. Railroads and telegraphs distributed one reference time across wide regions. After the International Meridian Conference of 1884, longitude, time zones, and a global reference framework became increasingly connected. Earth's rotation is not perfectly uniform. In the 20th century, scientists chose a more stable reference, a frequency associated with the cesium-133 atom. 1 second is defined by counting exactly 9,192,631,770 cycles of that radiation. The definition became international in 1967. Atomic time supports communications, electrical grids, financial systems, and GPS positioning. Behind the time on a phone is a worldwide effort to compare clocks and keep them synchronized. Shadows, water, moons, gears, and atoms look completely different. But every clock does the same thing. Find a repetition, count it, and make the result reproducible somewhere else. Timekeeping became a way to coordinate the future. When should we meet, depart, open a gate, or begin a task? A clock turns those plans into a visible agreement. To carry that agreement across generations, humans needed another invention, a way to place memory outside the mind. Next, we will follow the first traces of writing.